Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed that how you can calculate or determine the settlement of dry sand due to earthquake shaking. So, today I will continue that part and I will finish that part, and then I will start the saturated sand part. So, now first I have discussed that you calculate the strain effective. So, this and then strain effective into G effective divided by G max. This is the expression, and this is the chart by which you can get the shear strain. Now, once you get the shear strain, then from using this chart, either if you know the N160 or if you know the relative density, then from the shear strain you will get the volumetric strain. Now, volumetric strain due to compaction is given only for magnitude 7.5 earthquake, because it is a 15 cycle. Now, then we have to apply the magnitude correction factor. And these are the magnitude correction factor. That is, the factors are ratio between the volumetric strain at any magnitude divided the volumetric strain at magnitude 7.5. Okay, so now I will give you the steps. The steps is that you have, say, different layers, or in a single layer, say sand layer, you can divide it into number of sub layer. Okay, you can divide it into number of sub layer, and so that means you have different layers. Now, determine the thickness of that each layer, or you decide the thickness of that each layer. Either determine it, or if you have a single sand layer, then if you divide it into number of sub layer based on their n value, then you can determine or decide the thickness of each layer. Then measure the n value, or you have already measured it. So, that means you have n value or dr value. Dr means the relative density. Then you can measure the G max. Okay, you measure the G max or estimate the G max based on the N160 value. I will give you the expression, or I have already given the expression. You can use those expression also. Either you measure the G max of that each layer or each sub layer, or you estimate the G max based on the n value. Then determine the sigma V or sigma m dash at the middle of each layer or sub layer. Then determine these expressions, strain effective into G effective divided by G max by using these expression, 0.65 mx by G sigma V RD divided by G max. Now, once you get that, then you calculate the estimate the effective strain by using figure A. This is figure A. You determine the effective strain based on your using these effective strain into G effective shear modulus divided by maximum shear modulus into sigma m dash. Once you get that effective strain, then you estimate the volumetric strain by using figure B. This is figure B, either this or this. Okay, by using the estimated effective strain and the N160 or dr. Based on that, you calculate volumetric strain. Now, apply magnitude correction factor. If you are determining the settlement of the sand for magnitude either greater than or less than 7.5, then you have to apply the magnitude correction factor. Then, considering the multi-directional shaking, multiply the estimated volumetric strain by 2, because here we are calculating actually the vertical strain, but here our shaking, or sorry, we are actually considering your one dimensional shaking, vertical strain, actually vertical deformation we are measuring, but we are considering one dimensional shaking to estimate these equations or this process. Now our shaking is multidirectional, okay. So that's why you have to apply a factor 2 to the estimated volumetric strain, and then multiply the volumetric strain by the thickness of each layer or sub layer to determine or estimate the settlement of that layer, vertical settlement of that layer. Okay, settlement means vertical. Generally, settlement is vertical, lateral is the deformation. And add this each layer or sub layer settlement to get the total settlement. Okay, so now I was talking about the how to calculate the Gmax by based on the N160 value. So I have already given a few such expressions. Okay, so you can use those expressions, or you have any other expressions there. Those you can also use that because you can have to estimate the Gmax. That's it. But here I am giving another expression which is proposed by Seed and this in 1970, where Gmax can be calculated by 1000 into K2 max into sigma m dash to the power 0.5, where K2 max can be estimated in different way. First, if you have the N160 value, then you use the K2 max is equal to 20 into N160 to the power 1/3. Remember that here Gmax and sigma m dash both are in pound per feet square. Both are in pound per feet square. Okay. Now if you have the void ratio, then also you can calculate the K2 max. So this is the void ratio and these are the K2 max value. If you have relative density, then also you can calculate K2 max. So this is the relative density and this is the K2 max value. So once you either know the void ratio or the relative density or the N160 value, then based on that you calculate the K2 max, and then using this expression you will get the Gmax. Okay. So now I am giving one particular example, then you can see how we can calculate the settlement of dry sand for a particular site. So I am considering a soil, the same soil here, because of the ease of calculation. I am taking one particular layer with same n value, so that I can have the same Gmax value, K2 max value, and then I can have the different Gmax definitely with respect to depth. So now, but I have divided that soil layer into n number of 4 layers, sub layers. Suppose this is my soil layer, where this is say 8 meter thickness. Okay. Now that I have divided into 4 layers, because if you divide it into small segment, then it will be easier for you to calculate the more accurate result. So suppose your N160 is given, so that means first you measure the N value, then correct it by applying those correction factors, or normalize it, then convert it to 60% hammer efficiency, then apply other corrections also, then you will get the N160. So that value say 10. So this is same for all the layers. It can be different also. It can be different also. Remember that for different layers. Okay. And remember that there is a sand layer. So obviously this is a sand layer. There may be below that there will be clay. So we will consider only the sand layer thickness, and we will calculate the settlement of that sand layer only by this approach. Remember that. So now here I have to calculate the settlement for the magnitude of moment magnitude of earthquake M, and A max by G is equal to 0.25. Now here I want to mention one more thing, that I am here always giving the moment magnitude of 8. So suppose if you have the other magnitude with you, that is surface wave magnitude or body wave magnitude or local Richter magnitude, then I have given the charts or the chart is given. So you can use this chart and convert those magnitude to moment magnitude. And use of those magnitudes has some limitations. Follow those limitations also, then convert it to moment magnitude, and then you can use the moment magnitude, or directly you can measure the moment magnitude itself. So mx by g is 2.5 is taken. Unit weight of this whole layer is all the sub layers or all the layers is 18 kilonewton per meter. Phi value is 832 for all the layers. Okay. So I will calculate the G max by using the expression that is given here, K2 max into sigma m dash to the power 0.5, and unit, this is pound per feet square. This is also pound per feet square, because it is the empirical expression. Unit is very important. This is pound per feet square, this is also pound per feet square. Now K2 max, here the N160 value is known, so I will use that expression of 20 N160 to the power 1/3. That expression I will use. Okay. So here the unit I am giving that for 1 kPa is equal to 20.89 PSF or pound per feet square or square feet. Okay. So I will show you the calculation for one layer, and rest of the layers or sub layers will be done by the same way. Okay. So this is my layer, say 1. So this is layer 1. We have 4 layers or sub layers. Okay. So for layer 1, sigma m dash, because here m dash and m is same, because it is the dry soil, water is not present here, or if the water is present, it is far below that layer. So this is 1 by 3rd sigma v dash 1 plus 2 k0. Okay. So this is your sigma v dash will be how much? So that I am taking the middle of this layer, and every layer as a thickness is 2 meter. Okay. This is also 2 meter. Equal sub layers. So that means I am taking it for layer 1 it is 1 meter from the ground surface, and layer 2 it will be 3 meter, layer 3 it will be 5 meter, layer 4 it will be 7 meter from the ground surface, because I am calculating the middle of this layer. Okay. So that means sigma v here will be 1 into 18. So this will be 18 kilonewton per meter square. So here I can write 1/3 into 18 into 1 plus k0 is how much? 1 minus sin phi. So this is 1 minus 32 degree. This is 0.47. So this is 2 into 0.47. Okay. So it is coming out to be 11.64 kilonewton per meter square. So for the layer 1 is sigma m dash is 11.64 kilonewton per meter square. Now I can calculate the K2 max is 20 10 to the power 1 by 3rd, because N160 is 10, so it is 43. So that one used for every sublayer. So for G max, that is equal to your 1000 into K2 max is 43 into 11.64. That will be converted to PSF. Now 11.64 is KPA. Now that will be converted to PSF. I will convert that. I will multiply 20.89 to the power 0.5. So that is given is 670524 PSF, pound per square feet. Now that I will convert it to KPA. So that will give me 32098 kilonewton per meter square. So now for the layer 1, I know what is the Gmax value. So for every layer, Gmax value is changing. So Gmax value is a function of depth. Remember that, but not the function of strain. But your G value is function of depth also as well as the function of strain. Okay. So that means for G, now I will calculate this term, because if I go for the steps, you can see for different layers I have identified. I know the thickness of each layer. I know the N160 value for each layer. Then measure or estimate the Gmax that I have done for first layer. Similarly, you can do it for second layer, third layer, fourth layer. Next, I know the sigma V and sigma M dash at the middle of each layer. Then I will determine this term, strain effective into effective shear modulus divided by maximum shear modulus. So how I will do that? So I can get strain effective into G effective divided by G max. So that expression is given. So this is the expression, 0.65 into A max by G into sigma V RD G max. Okay. So I will use that. So 0.65 A max by G is 0.25. Then sigma V is 18 here and divided by G max. Then divided by G max, which is 32098, and RD value. So what is the depth? Depth is 1 meter. So this is the chart I am taking for M equal to or MW equal to 8. So RD up to 4 it is still 1. Okay, up to 4 nahi 3. Up to 3 it is 1. So 1 meter it will be 1 itself. When you go for the second layer, then also it will be 1. But when you go for the third layer, then it will change. When you go for the fourth layer, it is 7 meter. So 7 meter it will be around your 0.96. Okay, that you can use. So it is strain effective is coming out to be 9.11 into 10 to the power minus 5. Okay, 9.11 into 10 to the power minus 5. Now I have that sigma M dash is how much? It was 11.64 kilonewton per meter square. So that I have to convert it to ton per feet square. Okay, so that is equal to 0.11 ton per feet square. Okay, what is the conversion? That 1 kilonewton per meter square is equal to 0.00932 ton per feet square. Why I have to convert that? Because this chart it is ton per square feet square. Okay. So now let's see, calculate the strain. So you have, this is 0.11 ton per feet square, and this term is effective strain into G effective divided by G max is 9.11 10 to the power minus 5. So you go to this chart. So 9.11 10 to the power minus 5 is this one around here, and this is 0.11. So this is 0.11 ton per feet square. So 11 ton per feet square will be around here. This is 0.1, this is 0.2, 0.5, 1, 2. Okay. So it is, so this is the, if I draw it, then if I, so my effective strain will be roughly how much? So this effective strain value will be around 1.8. This is 10 to the 4. So this value is 1.8 into 10 to the power minus 4. It will be 1.8 into 10 to the minus 4. If I take it in percentage, then it will be 1.8 into 10 to the power minus 2 percentage in percentage. Okay. So this for the sub layer 1. Now if it is 1.8 10 to the minus 2, now I will go to this chart. With this chart it is N1 10. So this is the line. I have either I can use this chart or this one. Here I have N1 60. Then that's why I will use the right hand side chart. If you have relative density, then you have to use the left hand side chart. So now it is shear strain is how much? Shear strain is 1.8 into 10 to the minus 2. So 1.8 means around here. This is 1.8 into 10 to the power minus 2. Remember, it is in percentage. So now if I come here and then I will calculate the value. So from here, okay. So now remember that here this chart is going upward. This is 10 to the minus 4, this is 10 to the minus 5, minus 4, minus 3, minus 2. But this chart is going downward. This is minus 3, minus 2, minus 1, 1, 10. So that means this value is actually 4 into 10 to the power minus 2 percentage. This is 1, this is 2, 3, 4. 4 into 10 to the power 2%. So volumetric strain will be 4 into 10 to the power minus 2 percentage. So now if I write in a tabular form that my layer number, this is N160, this is the thickness in meter, okay. Then if I write this is sigma m dash in kPa, this is G max in kPa, this is effective strain into G effective divided by G max, okay. Then from the chart effective strain, then the volumetric strain in percentage, then to apply the, this is volumetric strain for M equal to 7.5. Now this is volumetric strain in percentage where M will be 8, okay. Then you have 2 volumetric strain in percentage because you have to multiply by 2. Then the settlement, that is in meter. So this is the table. Now I put for the first layer I am doing N160 is 10, thickness is 2 meter, sigma m bar was 11.64, G max was 32098. Now strain effective value was into this term was 9.11 into 10 to the power minus 5, okay. And I am getting effective strain is how much? 1.8 into 10 to the power minus 4 or 1.8 into 10 to the power minus 2 percentage, okay. Now volumetric strain, how much I have got? The volumetric strain is 4 into 10 to the minus 2 percentage. 4 into 10 to the power 2 minus 2 percentage. So, this is 4 into 10 to the power minus 2 percentage, but remember that that is for your moment magnitude 7.5. Now, we are designing for 8. Now, what is the value I will consider? Factor. So, for 7.5 it is 1, say 8.5 it is 1.25. So, for 8 I can take 1.125. Okay. So, that is why for 8 I am taking 1.125. Okay. That I am taking, because this is the magnitude under which I am designing. So, but here it is, we have to multiply it 1.125, but if it is less than 7.5, then you have to reduce that volumetric strain, obviously. Now, we are actually measuring it is 7.5, but now we will use it for 8, so we have to increase it, so we have to multiply it with 1.125. So, if I multiply it, then it will be your 4 into 1.125 into 10 to the minus 2. So, that will give me 0.045. Okay. Now, you have to multiply the 2. So, that means here it will be, again it is in percentage. It is in percentage. So, if I multiply it by 2, it will be 0.09 percentage. Now, the settlement, I have to multiply it by 2 meter. So, 2 into 0.09 divided by 100. Okay. So, because it is in percentage, so it will be, so settlement, how I will get? Settlement is your 2 meter is the thickness into 0.09 divided by 100, because it is in percentage. So, it will give you 0.0018 in terms of meter. In terms of millimeter, it will give you 0.018 millimeter. Or in terms of millimeter, sorry, it will be in terms of millimeter, it will be 1.8 millimeter. So, I am keeping it in terms of meter itself. Now, the same process I will follow for the other layers. I am not showing that calculation, the same calculation, only the depth will change. Initially, for layer 1, I determine everything at middle of the layer, 1 meter. For layer 2, I will go for 3 meter. Layer 5, I will go for 5 meter. Layer 6, I will go for 7 meter depth. And rest of the things are same. I will follow the same process. Okay. So, that means how I am getting this? This is actually 2 into 0.045. So, that calculation I have shown here, I will get from, I will get from figure A, and this one I will get from figure B. Now, then you convert it, the multiplying factor I will apply, magnitude correction factor, then I will multiply it by 2, then I will multiply the thickness, and then divided by 100, I will get the settlement for unit area. Remember that. Now, I will do quickly. I will do for the other layers. For layer 2, the N160 is 10, thickness is 2 meter. Then I will get the sigma m dash is 34.92 at 3 meter, middle of that layer 2. So, and I will get G max is 55595. Effective strain into G effective divided by G max is 1.6 into 10 to the power minus 4. Okay. Then this effective strain I will get 3 into 10 to the power minus 2 percentage from figure A. Then volumetric strain I will get as this is after multiplying the correction factor directly. I am getting that volumetric strain after multiplying correction factor. This will be or this will be 7 here. So volumetric strain that I am getting here, it is 7 into 10 to the power minus 2. Okay. Then after multiplying the correction factor 1.125, I will get it 0.0788 percentage. Okay. Then I will get into 2, I will get 0.1576, and then the settlement will be 0.0032 meter. That is for layer 2. Similarly, for layer 3, this is 10, this is 2, sigma m bar is 58.2, then G max 6771773, then this term is 2 into 10 to the power minus 4, then effective strain I will get 2 into 10 to the power minus this term, then the effective strain will be 3.5. Effective strain will be 3.5 into 10 to the power minus 2 in percentage, and this volumetric strain is 10 to the power 8 into 10 to the power minus 2, and if I multiply I will get 0.09. From there I will get 0.18, and the settlement is 0.0036. Okay. Now for layer 4, so this is 10, this is 2, then this value is 81.48, then G max is 84923, then this term is 2.3 into 10 to the power minus 4, then effective shear strain is 4.2, it is in percentage. Okay. Then volumetric strain is 0.1 percentage. If I multiply, I will get 0.1125 in percentage into 2. I will get 0.225. Then the settlement is 0.0045. Okay, so now if I add this total settlement, if I add the settlement of all the layers or sublayers, I will get 0.0131 meter. So my settlement is 13.1 millimeter. So that is the settlement of the dye sand for this particular layer that I have considered. So this way I can calculate the settlement of a dry sand layer under seismic checking. So in the next class I will show you that how we can calculate the settlement of a saturated sand under seismic checking, and then I will start the liquefaction mitigation or seismic mitigation techniques also. Thank you.